Okay, so today I handed back some homeworks. I think we're all up to date now on the grading. And you did have a homework assignment due today, which is, I think it's the growth of functions, right? You had to do some big O's and big omegas and therefore big thetas and stuff like that there. So how was it? Questions? Yes. Well, some of them were and some of them weren't. Some of them you have to think a little, do a little analysis yourself.
So,
the one with the log base 2 thing, you mean?
no, not that. The first one.
The first one?
Yeah.
Big O?
Yeah.
And big omega?
Yeah.
What was the, what?
Because I feel like, because you have more ends. Can you just drop
Well, you just have to be creative. Like I said, I did an example of being creative, and you just got to be.
So there's no like one answer then?
Oh, that's a good question, actually. There is not more than one answer. There's more than one way to skin a cat, as my father-in-law used to say.
So we can have different C values.
You can have different C, but a different C would be what might give you a different N naught. Yeah. So that's a good point. There is not just one way to do it. So in general, yeah, like if it's let's think about this. If it's an upper bound, if your C is really big, your N naught might be low. I think that's right. I think that's the right direction.
And not.
My C is 1,000,000 and something.
It could be 1,000,000 and something. It doesn't, as long as it's a constant. As long as it's a constant.
Yeah.
It's a constant. So it has to have a specific value. Can't be a variable. Any questions over here at all? You guys got?
By graph. Or do we have
Well, I said you could use B, C, or D on that, right? So that's what you can use. You can quote, you can say because, whatever, and use that, yeah. Yeah, I had you graph that out just to show that it was. And the reason I gave you that with the logs is because those are very common in, those come up all the time whenever you do statement execution counts. We didn't do statement, actually, all of this growth of function stuff, this comes from doing statement execution counts. Have you done those in your programming class?
No.
Well, yeah, we don't have time to do it here. We could do it in GCL. We could do some statement execution counts, but we don't have time. But that's what you should learn how to do that in your other courses. And then what happens is when you do a statement execution count with something that has loops or that has a recursive call, then you get an expression for this n, like instead of having 2n squared plus 3, you might get like n log n something, or plus n or something like that. So when you count those, and then when you do the statement execution counts, those are directly related to how long it takes the program to execute, because each statement takes a certain amount of time. Yeah. So that's where these functions come from. So it's directly related to programming, analyzing the performance of your programs. Okay, any more questions? Did you still have?
We do.
relates to B, C, and D?
Well, I mean, you should, to prove that 2n squared times 2 to the n plus n log n is big theta, you have to prove that it's big O, and then you have to prove that it's big omega. So, but you do that, you don't do that by graphing, you do that line by line like we did before.
Oh, okay, so you do have to prove that.
Oh, yeah. Yeah, you have to, so the first thing, well, first you yeah. So to prove big O, you have to show, so to prove big O, you have to show that 2n squared, you have to show that there exists a positive C and n naught such that 2n squared, 2 to the times 2 to the n plus n log n is less than or equal to C times n squared 2 to the n, n squared 2 to the n, for n greater than or equal to n naught. So you have to come up with an n naught and a C.
Yeah, got that. One should be the first step. Start on the left-hand side.
Well, let's start with the left-hand side.
Yeah, but I gotta stop.
Well, I think the less than or equal to,
It's not intuitive.
well, Well, what do you know about n and n squared? What do you know about,
They're positive.
yeah, so here's the proof. So it must show blah, 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 and then here's the proof.
Yeah.
So you would start with 2n squared, 2 to the n, plus n log n. And you got to do a bunch of stuff down here, and in the end you got to get c n squared 2 to the n. Right? And here there has to be a bunch of equals and what? Less than or equals to, equals, less than or equal to, whatever. Okay? So this is where you are, this is where you have to get.
Yeah, I know. Can you give me a hint?
Well, let me see, less than, huh? Well, probably what you should do is change
You
this.
can change that into a...
If you can get this up, you know, okay, here's what you have to do. Somehow you have to increase, look,
Yeah.
somehow what you have to do is
Turn that into that.
make this something bigger. Make this something bigger than what this is, right? And then this whole thing will be less than or equal to that. So here's your hint. What your hint should be is, have this here. No, look. Okay, I'll give you a specific hint. Listen to this. I'll give you a specific. This is less than or equal to, and what you should do is, have this be less than or equal to something by virtue of making this bigger than what it is. Right? If you make this bigger than what it is, then this will be less than or equal to this.
I got it.
In other words, this will be less than, I'll give you one more hint. This is less than or equal to 2n squared, 2 to the n, plus, and this should be something that's bigger than this.
Turn that into an n, because you know n is greater than... Yeah, because of my data.
Yeah? Look, all of these proofs, look, I mean, anytime you do a proof, the thing that you want to do is you know where you start, figure out where you want to end, and then figure out kind of how this has to be, and then reason how, okay, well, how do I get from here? I mean, this is just like all the other proofs we've done. It's pattern recognition, you know. Only here you're recognizing quantities that are bigger, you know what I mean.
If that gap was n squared, could you group them together? Mathematically?
Well, you do whatever math, as long as it's legal math.
No, I forget because it's...
Whoa, you mean you forget algebra? Well, I mean, you know, if you do n squared x plus n squared y, you know that by math is n squared times x plus y. Yeah, you gotta. That's how you factor out, right? But I think what you want to somehow you want to have n squared 2 to the n also. I mean, you know.
Yeah.
Yeah, these are good. I like these proofs because it's not just this mechanical thing. You've got to be a little inventive in the way you do these inequalities. And of course, to go the other way around, to make it greater than or equal to, well, it depends on whether this is positive or not, right?
N can be anything, right? What are the two values at the end that you have to set equals to n sub 0?
C and n sub 0. And both c and n sub 0 have to be positive. It's okay for c to be negative. Sorry, no. It's okay for c to be less than 1. But they both have to be positive. Well,
The proof is your reasoning.
the proof is the reasoning. And anywhere in the proof, if you say provided n is greater than or equal to, like, I don't know, 76, then in that proviso, you're saying, oh, n naught is 76.
What if we just say greater than or equal to 1?
Yeah, then it can be 1, yeah. It's certainly possible to have n naught be 1. And see, here's an example where you can't use that polynomial theorem. What was that? Remember that polynomial theorem? What was it? Oh, the asymptotically. Here you can't use this asymptotically positive polynomial, right? So it's a good thing you know how to use these techniques, right? Because you use the exact same techniques when it's not a polynomial. It only works for polynomials, but you don't always have polynomials. So that's why it's good to know how to do this. For the last one, no proofs, you just yes or no.
Sweet.
I have actually had some people, the only way that they could figure that out would be to actually prove it. So they try to prove it, you know, and then they can't. If they can, they say yes. If they can't, they kind of see why they can't, and then they say no. But there's actually a way to figure out without proving.
Can you tell us how to do that?
Well, no.
Oh, we've
let
already
you-
done it. So.
Well, I'll tell you when you hand it back. I'll tell you when I give the homeworks
I'm not
back.
going to be interested then.
You're not going to be interested then. Come on. You're going to be interested in this for the rest of your life. This is such great material. Oh, that's funny. Okay.
Glad you think so.
Okay, any more questions on homework? All right, now today we're going to continue with a theory of integers. And like we explained last time, we're just going to jump right into the middle of the chapter. And last time we looked at the definition of min and max. And we saw, and what did we determine? The min and the max, are they abelian monoids, yes or no?
No.
Correct, they are not. What property do they not? What property do they lack? They do not have an identity. So that means that any quantification, we can quantify, but only with the restriction that you can't use like the empty range rule, because the empty range rule depends on the operation having an identity. So you can't use any quantification where the range is false. So here we have this restriction. Although min and max are symmetric and associative, they do not have identities over the integers. Therefore, axiom 8.13, empty range rule, does not apply to min or max. Also, when using range split axioms, no range should be false. So as long as you follow those restrictions, we can still do it with those restrictions. All right. Now, 15.56, idempotency. Here's an example. X min x equals x. Right? The minimum of x and that's not an example. That's the thing. The example would be 5 min 5 equals 5. Right? And, you know, same thing, negative 3 min negative 3 equals negative 3. Okay? So that's an example of min. And now, and let's take a look. There, somebody mentioned or pointed this out in 15.53. It's the definition of min. Now look at the definition of min. This is kind of interesting because the definition of min is, it's not like we have x min y equals something. It's not in this form. Do you see what I mean? Let's consider that. Let's look at that a little closer. X min y does not, the definition of x min y, it's not x min y equals something. This is what the min of x and y is. It's not in this form. Instead, it's for all z, right? And then range true. And then what do we have in the body? Z is less than or equal to x min y equivales z is less than or equal to x, and z is less than or equal to y. So this is in the form of a for all z. Definition in the form of for all z. Okay, so here's the thing, you guys. Whenever we want to prove a property of min or max, the way we do it is kind of like the way we did the 9.8 lemma. What we do is we say, let z be an arbitrary integer, and then we prove that what? Z is less than or equal to x min y equivales z is less than or equal to x, and z is less than or equal to y. You see what I'm saying?
Prove using the definition.
Well, the way we use the definition of it is we say, let z be an arbitrary. We can't say, like, to prove something, we can't, well, here, let's just take a look at an example. Here's one we're going to prove. We're going to prove 1554, symmetry. All right? So we're going to prove x min y equals y min x. Well, we can't just start with x min y equals blah, 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 blah. And then in the end get y min x. We can't do that.
Can
We,
we
we-
use the body of the quantification?
that's what we have to do. But the thing of it is that the body, I mean, it's a for all z. You see what I'm saying? So that we don't have to keep writing down for all z, for all z, for all z, we'll just say let z be an arbitrary element, and then we'll prove that.
Prove just the body.
And then we'll prove just the body. So that we don't, you see what I'm saying? So that we don't have to do that, all right?
We're just going to use symmetry of and, right?
Yeah, and that's how it's going to work. But here's how, so let's go ahead and prove that with setting it all up the way it needs to be set up. Okay, so let's prove 15.54, and the thing that we're going to prove is x min y equals y min x. Okay, so the way we set it up is the same way we set it up for proving the 9.8 lemma. We say let z be an arbitrary integer. Are you with me? We'll say let z be, and then we must prove what? Z is less than or equal to x min y.
Equal z.
No, we want to prove that this equals this. So we have to prove that z is less than or equal to x min y equals what?
Z is less than or
Equal to
y min x.
y min x, because that's how it would be the min of the. It must prove is z is less than or equal to y min x. But then what we use, and
I would have worked either way. I was thinking.
yeah, okay. Is everybody clear on this?
Yes.
On how we set this up? So we start with, so here's the proof. And so z is less than or equal to x min y. And now we say this equals by definition 15.53. Yeah. And so what does that so what by that equals what? If z is less than or equal to x min y, well, for all z that equals
Z is less than or equal to x.
z is less than or equal to x,
And z is less than or equal
and z is less than or equal to y. And then this equals by what?
to symmetry of and.
Mm-hmm.
3, 4.
3, it's 36.
Yeah, that's close.
Yeah, pretty good. And so what is it by symmetry of n? That's what? Z is less than or equal to y, and z is less than or equal to x. And then this equals by definition 15.53 with xy replaced by yx. Z is what? Less than or equal to y min x, and we're done. Now, does everybody see how that works?
I'm curious in the definition of min and max. Is this just the way it's designed? Because, for example, z could be something that's less than both x and y.
Yeah, yeah. Actually, that's a good question. And in fact, here, let's explore that. Yeah, let me show you. Let me show you an example of 815. Because it could be less than both x and y, couldn't it? Okay, yeah. Okay, but the thing of it is, the thing that makes it work is it's for all z. It's not that there exists, see. Okay, so let's do example. So, all right, so your question was about an example of 1553. Okay, so example of 1553. Okay, so let's use some specific examples of x and y. Let's do 5 min 3. Okay. So what does 5 min 3 mean? It means that for all. So what is 5 min 3? 5 min 3 is the number such that what? Such that for all z range true, z is less than or equal to 5 min 3 equivales what? Z is less than or equal to 5 and z is less than or equal to 3. All right? So this is what's true about 5 min 3. All right? So let's think about it. Is this really true for all z? Well, let's do a couple. How about if z is 10?
No.
Well, wait. If z is 10, then z10 is less than or equal to 5 min 3 would be what? False. But then 10 is less than or equal to 5 and 10 is less than or equal to 3. That's what? False and false. Are you with me? So we would have false equals false, so that would hold for z equals 10. Are you with me?
Is false and false is still false? Yeah, okay.
So it's
Yeah.
4.
Okay, so here. Let's do, so here's z equals 10. This is false equivals false and false, right? Now let's do z equals 4. What would this be? False equivals true and false. Oops. And true and false, right? But that also holds, right? And let's have it be here. Let's have it be 3. Then what would this be? True equivals what? True and true. And let's have it be 1. True equivals true and true. See? So for all z, it's always true. But now we knew in our head that 5 min 3 was 3. Right?
Yeah.
So this is an example. Yeah. So it works for all. This works for any value of, for all z it works. And furthermore, think about it. 3 is the only one for which this works for all z. Are you with me?
No.
Well, can you think of another number for which this would work? In all cases for all z. See, here we knew, look, we knew the answer here, we knew the answer of 5 min 3. We knew that was 3, right? And when we used 3 when we did, when we did this, right?
Yeah.
I'm saying there's no other number for which this is true for all z other than 3. Well, try
What
it.
about 1?
Okay, well, we did 1. True equals true and true. So that works.
I'm sorry.
Then why are you saying that?
Oh, no. Hold on. If you said 1, if you claim that 5 min 3 was 1, then this would be 1, right? So this would be 1, right?
Yes.
So if you put 1 here, that doesn't work, right?
Well, not necessarily. It can still
Yeah, but it has to work for all of them. I can find one for which it doesn't work if the min is 1. If you claim here, if you are claiming that this is 1,
No, I'm claiming that that's 3, but z is 1.
Keep going, guys.
no. Well, that's my point. For 3, it works for all of them. But what I'm saying is, I'm claiming that 3 is the only number for which this works for all z. Are you with me? But on the other hand, if you said no, it should work for 1. Well, so you're claiming, if this is 1, I'm saying that if this is 1, then this does not work for all z.
So if you put 3 in, it wouldn't be less than or equal to.
Just spread out all over the place.
Yeah, so 3, this would be false, but this would be true and true, and then it wouldn't equivalent.
Okay, and so what about if 5 min 3 was like 10?
Okay, 10 it still wouldn't work.
I just want to see it.
All right,
I know it's not.
okay.
And then I put in something like 1. Wait, no, like 8. Okay, alright, that doesn't work. Okay.
All right, so now actually going through that little exercise is really how you get to the heart of the meaning of this, of the definition. Yeah.
Basically
So
saying 3 is the best answer and needs to be.
It's the only
Every
one
time that it will always.
that will work for all z. Yeah. But it's a little, it's yeah. So it's like I said at the beginning. It's not x min y equals something. It's z is less than or equal to this has to equivalent this for all z. That's the definition of min. Yeah. Let's take a look at how you can quantify and how the quantifications work. Yeah, here's an example of distributivity. Example of 8.15 where, let's take a look at 8.15. Remember distributivity? Star x range r body p star x range r body q equals star x range r body p star q. Okay, so just to show you how this works with max. Example. Yeah. Example of 8.15 with max. So check this out. 8.15 says, so 8.15 with the star being max would be max over x, range r, body p, and then max over x, range r, body q equals max over x, range r, body p max q. So let's do it for these. Let's let r be, or here. Let's have the range be 0 less than or equal to x less than 3. And let's let p be 3 times x. And let's let q be x plus 2. All right? And let's do the left hand, we'll do the left hand side and then we'll do the right hand side. We'll just, okay, so, and we'll see that they are equal. So the left hand side. So the left hand side is what? Max over x.
0 is less than or equal to x,
Less than 3. Body 3 times x. Max. Max over x.
Range 0 is less than or equal to x, less than 3, body x plus 2.
Okay. Now, what are the possible values of x? 0 less than or equal to x or less than 3. 0, 1, and 2. And so it's 0, 1, and 2. So the possible values of 3 times x are what?
0, 3, and 6.
0, 3, 6. So this whole thing turns out to be 0, max 3, max 6. Now, is everybody with me on that? No?
I can't see. You're standing in front of it, so I couldn't.
Oh, sorry. Yeah, I'm standing in front of it. Okay, so this.
So it can be 0, 1, and 2.
Okay, so x can be 0, 1, and 2,
So then you
which means 3 times x. The possible values of 3 times x are 0, 3, and 6.
Okay.
And then the operation is max, so it's 0, max 3, max 6. Yeah, that's why I'm doing this example. It's a little.
How can we keep the maxes? Just because that's what the operation.
Well, that's what the operation is. Remember on all these. Like if this were sigma, this would be plus.
Okay.
If this were pi, that'd be times. If it's max, it's max. Are you with me? Now, what about this one? The possible values of x are, oh, do I have an extra paren?
No, that should.
Oh, this should be a line.
So this is gonna be 2, 3, 4.
So this is 0, 1, and 0, 1, and 2. So this is, yeah, 2, 3, and 4. So this is 2, max 3, max 4, right?
Is max distributed?
Yeah, this is distributivity. Okay, so this is 6 max what? 4, which makes this whole thing what? 6. Now let's do the right hand side. So the right hand side would be what? max over x,
0 less than x less than 3.
0 less than or equal to x less than 3.
Body 3 times x.
Body 3 times x, max
X plus 2.
x plus 2. Hmm?
Do you have to have 3 times x in x plus 2 in parentheses?
No. I think if you look on the, oh, we should check that actually. I hope that max is lower precedence than multiply and addition.
It does.
It is, it's g.
Good, good. Oh, that was a nice check. G on the table, huh? Okay. All right, so what are the possible values of x here?
0, 1,
0, 1, and 2. So if it's 0, what do we have here?
2. 0 max 2.
Yeah, 0 max 2. So this would be 0 max 2. Are you with me? And then what? Max. Then what? 3 max 3. All right. And then max what? 6 max 4. Okay. Well, 0 max 2 is what? So this is 2 max 3 max 6, which is 6. It's the same thing. So you see that this shows how max can be used in these quantifications. As long as the range, notice that the range was not false. As long as the range is not false, everything works. Are we good? Okay, sports fans. Oh, do we have a big game tonight? Sports fans.
Oh, yeah, isn't it Final Four?
Yeah.
Like, Final
Well, yeah, the final 2, that makes it the championship.
Butler, UConn?
Yeah. Yeah.
You guys gonna walk the
No, but
Boy, it sure would be the Cinderella upset,
yeah.
wouldn't it?
Oh, yeah.
Man.
8 seed?
Yeah. Okay, now, you guys, as long as we're going back and reviewing things, let's go back a little bit further to 3.73.
No.
Check this out. Check this out. 3.73. Okay? What we're going to do, now, for some reason, I'm not quite sure why this is the case, but for some reason, these proofs with these theory of integers, we use this new, I think we've used this, I'm sure we've used this proof technique before, but let's review it. We're going to use the 3.73 proof technique. Okay, 3.73 says this. Says what?
true implies P equals L.
True implies P equals P is correct. So, are you with me on this? Now, I think we've done this once or twice before, maybe. So, in order to prove P, we can just prove what? True implies P. And once we do, if we prove true implies, then we've proved P. All right? So, to prove P, do you remember this?
I feel like we've done it when we pulled rabbits out.
I think we did this once before, yeah.
We did it once.
To prove P, prove true implies P. Once we do that, we've proved P. Yeah? All right. Now let's go all the way up to 1579. Well, let's review this a little bit. So we just proved a symmetry. You can prove associativity. We can prove idempotency. 1577. Oh, now 1577, actually, is the definition of divides. Now, I think we've done this before.
We made it.
I think we use this, yeah, we've done this a lot, haven't we? Divides, we've used divides. Well, here it is. It's in an axiom. Definition of divides. C divides B, equivalves, there exists a D such that C times D equals B, right? Now, and what we're going to prove, so that's, do we prove 1577, yes or no? No, because it's a definition. 1578, however, is a theorem. C divides C, right? Now, so we're going to prove 15.78, but we're going to use this technique. So, prove 1578. And, but we're going to use this technique. So we're going to say by 3.73 will prove what? True implied, yeah. Well, we are going to use the definition right off the bat, but we're going to have to show, you'll see, because that's a there exists. Because that's a there exists. Yeah. So here's what we're going to do. We're going to start with the right-hand side, and we're going to get it to follow from true. Are you with me? Okay. So here we go. Here's proof. But we're stating here what we're aiming for, right? So the proof here is, we'll start with C divides C. Now this equals by what? So now you just got through telling me.
1577.
1577. Definition of divides. So it will be, there exists a D, range true, such that what? D times C equals C. All right, you guys. Now what? But how do you say use one? I mean, what step is it?
Divide, use math. Divide C from both sides.
I will give you a hint. It is 9 point something. Got your equation sheet?
Yeah, it is.
No. Existential double trading would just switch them around.
It's 9 something?
Yeah.
Oh.
914.
And it has to do with their exist, because
Some kind of trading.
the problem is we got to get true here, but here we have an exists. How can we get a true? How can we get rid of the of an exists?
By generalized order?
Instantiation.
Well, but then you'd have a for all. Then how would you get rid of the for all?
Instantiation.
Oh, well, instantiation. No.
That's how you get rid of it.
Oh, that's how you get rid of the for all. But we have a there exists.
Reverse one for exists.
Well, which one was that?
Isn't it called instantiation?
No, I think the instantiation was the for all.
Probably the same for both.
That's 928. That's the opposite way.
Oh, wait. Hold on. You have something there. 928. What did you say?
Introduction. Yeah, it's a follows.
Yeah, it's the follows. Yeah? Are we good? I think they discovered it. All right. So what does this do? This follows from using what? Epsilon introduction. Epsilon introduction 9.28. But wait a minute. When we use 9.28 epsilon existential introduction, I said epsilon, I meant existential.
Replace the dummy with anything.
Yes, you can replace the dummy with anyway.
Let's replace it with C. One. Just 9. Oh. Both would work. Oh, I know.
Okay, so let's so let's use epsilon existential introduction with P. E is the expression, right? Are you with me? P, E, and X replaced by what? So now what are we using for P, E, and X? Yeah, the P is,
The body. The body.
yeah, C times D equals C, right. C times D equals C, all right? And then for the E, what will that be?
Uno.
1. And for the X, what will that be?
D.
D. Very good. Oops, wrong.
Sick.
Well, and what do we get here then?
D times C equals C.
True one, but not math.
No, what?
You should quote and math and just say true.
No, let's,
We're gonna have to,
1 times C.
C times
No, 1 times
No,
C,
it's
not C
D.
times 1. 1 times C.
is it 1 times C?
It is 1 times C.
Oh,
Are you doing text with substitution?
Even though it's
yeah, I'm doing
And TS in the hint.
Yeah.
Yeah, and TS.
You should probably write that.
Okay. Well, you get counted off if you don't put,
So it's 1 time.
if you don't put monotonicity. But you don't have to put
For this?
TS. No, I was saying,
I go.
no, there's no monotonicity in this, sorry. And TS. Okay, so what is it? 1 times C?
1 time C.
Which equals, by math, true. Well, and we know reflexivity of equals, right? And that's it, because that's what we wanted. Yeah? How about 15, okay, so that's 1578. 1579, C divides 0. 1580, 1 divides B. 1 divides anything, right? 15.80.1, negative B divides C equals B divides C. 15.80.2, negative 1 times B, or sorry, negative 1 divides B. And 1581 is C divides 1 implies C equals 1 or C equals negative 1. And 15.81.1 is C divides 1 equivals C equals 1 or C equals negative 1. So not only does it imply it, it equivals it. And now 1582 is the other one we're going to prove. D divides C and C divides B implies D divides B. But it's going to take a few minutes to set that up, and well, let's set it up since we have a few minutes. And I think we did it once. I'm on record, I can prove it.
But sometimes because the video is short.
True. Yeah.
No. On one I quit. On one I actually quit early, and I said, "You owe me some."
We have like 2 minutes.
We have 2 minutes.
We're just gonna have to
Okay.
summarize
All right.
and review.
Now, okay, you're right. Okay, so
By
now,
popular request.
okay, by popular request, and now it's on video. We are quitting class early,
Oh, not
A minute and a half over.
I didn't film that last part, sorry.
and and we'll see you tomorrow.